Well, good day, it's Charlie ZL2CTM. Happy New Year to everybody. And firstly, thank you very much for all those who send in some comments on the last video in terms of ideas and thoughts for what I might want to look at in the next few months. What I did want to have a bit of a play around with is a power amplifier based on the BD139. I made a comment in the last build for the single sideband transceiver over the back there that the LD MOS devices, while it was certainly interesting to use, were obsolete, which was a bit of a disappointment. And one of the things that I have been trying to do for a lot of these radios, to a certain extent, is to use commonly available parts rather than sort of exotic parts. So with that in mind, what I wanted to play around with was a bit of a test bed, I guess, using 4 BD139s in a push-pull arrangement, 2 in parallel obviously, just to sort of see how much power I could eke out of this arrangement with a 13.8 volt VCC. So I'm not going to try and do anything special in terms of doubling 28 volts or the like, but just to see what could be done, like I say, with 13.8 volts and some BD139s. So right or wrong, this is what I've sort of just playing around with in regards to a configuration. There goes the 4 BD139s. I've elected to put in 1 ohm resistors in the emitter leads. These are not matched devices, so my thinking there is by having those 4 emitter resistors, then I can sort of equalize, or they'll self-equalize how much current sort of passing through each device, so no one device will be hogging all the current. Right, so we've got 3 transformers, an input transformer here which has got a split secondary, which will be providing the DC bias for the 139s, being BJTs, the current devices, therefore I need to provide some variable current to them. T2 will just be a standard 10 turns, which I've got written down later on, 10 turns on a T50-43, configured that way to provide the VCC to the collectors, and then a final T3 there to match the output impedance to our 50 ohm load. By way of bias, I tried 2 different things, pros and cons. This is a very simple biasing system which I've used before, a 4001 forward biased at this point here with a variable resistor, and then by varying that resistor you can set how much current is passing through the 4001 and also the parallel devices there, the BD139s. The other circuit I tried here is a standard sort of circuit using a tip 41C to do the voltage dropping, and then a control BC547 with a small trim pot here, 1K trim pot, to vary how much bias comes out of there, and it's about 0.7 to 1.1 volts comes out of that with a variable current through the tip 41C. And then that resistor there R either is 1500 ohms or 220 ohms. When I was playing around with 150 milliamps biasing current, I needed to be 1500 ohms, yet when I was getting up into the, as you'll see later on, 400 milliamps, it needed to be 220 ohms. Now, in terms of the BD139s, again, I've chosen the BD139s because they're cheap and cheerful, easy to get hold of. They have an FT of 250 megahertz, a power dissipation of 8 watts. So I'm sort of kind of thinking that even if you ran them at half their maximum power dissipation, or 4 watts, therefore, maybe perhaps 4 on 4, and then in parallel with another 8, could you get sort of 10 watts plus out of it? I don't know. An IC max of 1.5 amps, and then a maximum VCO of 80 volts. Noting in this particular configuration here that the collective voltage for any one BD139 could be a up to twice the VCC there, assuming a perfect match on the output. So that's what I essentially have wired up as a test circuit. Now my initial thoughts for the transformers, there's a few things that were going through my mind, and I'll sort of talk them as we go along. We have devices in parallel, so if you're looking in here for any one particular side, this input impedance, or we'll call it Rin, is in parallel with this Rin. So therefore at this point looking in, it would be, I think, and we're going to have a bit of play around with that, would be half of, the total would be half of any one. And same thing looking backwards in here, you've got two output impedances in parallel, so therefore what we're seeing here, looking into any one particular side, would be half of one. So for a start, I'm going to ignore the fact that they're parallel devices. And right or wrong, and I should have said too, another thing what I want to do with this video is open it up as a discussion. So hopefully in the comments we can have people who are a lot more knowledgeable when it comes to power amplifiers, maybe sharing some of their knowledge and good ways to set these up. But for me this is very much a playing around and sort of, I guess, trying to get a better understanding of these, you know, how these amplifiers work. So anyway, right or wrong, I'm going to run with Rin equals beta AC, brackets little re plus big Re. Big Re because those emitter resistors are not bypassed. I've just left those as they are. Beta AC is our FT divided by our frequency of operation, so 250 megahertz, and for argument's sake I'm just going to do the initial tests at 7.1 megahertz. Gives us a beta AC of 35. Plugging in, and then for just somewhere to start, 100 milliamps biasing current per device, plus our 1 ohm for Re, comes out at 44 ohms. So therefore 44 ohms per side, or 88 ohms looking in from base to base. And like I just said here, I'm going to ignore the fact that there's parallel devices and just see what happens. So therefore now we're trying to match our 50 ohm input to 88 ohms base to base. So it gives us an N of root 88 over 50, or 1.32. So we'll give it a go of pretty close here, a turns ratio of 3 to 4. You mentioned before T2 is just 10 turns of bifilar windings on a T50-43. And looking at that, it looks about 24 gauge on that. T3, so our output transformer, if I'm correct there, for any one device, our output load that it needs to see for one particular device is VCC minus V saturation squared over 2 times power out. I'm going to assume, just for interest's sake, V sat of around 2 volts. So 13.8 minus 2 all squared divided by, again, for each individual device, I'm going to try and run them around 4 watts, so 2 times 4. Gives us a for each device a load resistance that it needs to see of 17.4 ohms. Double that, so 34.8 ohms will be the collector to collector. Again, I'm going to ignore the fact that there's parallel devices. So now we're trying to match now our 34.8 ohms collector to collector to our 50 ohm load. Gives us an N of 1.19, which is pretty close to a transformer with a primary of 5 and a secondary of 6. So that's what I'm going to try. So what we have now in terms of a test setup, we've got the amplifier there. The output is running straight into a dummy load. There is no low pass filter to clean up any of the odd harmonics. And we're just scoping the output there. We've got the input coming from the SIGGEN. We can see down there we've got our T1 of 3 turns to 4 terms with the center tap on the secondary to provide our biasing to the 2 sides. Our T2 there, our 10 turns of bifilar windings, and then our output transformer there. I initially, and you'll see later on, we'll use a binocular core, but for this one here, because I had so many windings, 5 and 6, I just couldn't squeeze those into the particular binocular core I had. so I've just run with a T50-43 toroid there. And the biasing network down here, that's not going for the simple diode biasing. The simple diode biasing works really well. In fact, it's really effective if you want to have a current of around sort of 150 odd milliamps and above. In fact, yeah, 150 milliamps and above. The only thing you need to worry about is that series resistor can get quite warm, so just going to make sure you've got the right wattage on that resistor. But for this one here, I'm going to use the tip 41 biasing network there. For the VCC coming in, just running that through a 0.1 ohm resistor there, and then just tapping the voltage across that to determine what the current is going through it. I mentioned it before. I just don't want to risk popping the fuse inside the meter, so this is just a nice easy way of measuring that. We got the scope up there, power meter, scope, and our input SIGGEN, so 7.1 megs, currently on 0 volts peak to peak, so we should be able to see everything there. If we were to turn it on, and we can just check. Got a total biasing current here of 39 millivolts, so that equates to 390 milliamps. You'll notice too that at the moment that biasing network is not temperature compensated, so that might creep up slightly, but it's pretty close to, and it will probably settle on later on, our 40 millivolts, or which is the equivalent of 400 milliamps. So that's at 100 milliamps per device. So 1, 2, 3, 4 output there. So we can start to increase our drive. So that's sitting on 10 volts peak to peak coming in. So 10 volts peak to peak should be 250 milliwatts. And we're outputting there, let's make sure that's in view. So there's 5 watts. So that's not too bad. And if we were to increase it right up, we sort of, as far as this SIGGEN will go, I can't go much further than 20 volts. Well, I can't go further than 20 volts peak to peak. And we're sort of sitting on around 6. And I think I did the maths before at 6.78. So 6.78 at 20 volts peak to peak. But like I say, at 10 volts peak to peak, or that 250 milliwatts, we're getting 5 watts out, which should give us a gain of 13 dB. Right, so that's the initial plan. What I'm going to do now, I'm going to pause the video, and then I'm going to redo the calculations for the input. Let me just turn that off. Nothing abnormal at all. Redo the calculations for the input transformer and the output transformer. Now we're actually taking into consideration that we have parallel devices, and we'll see if that makes any difference. So we'll be back soon. Okay, so now if we were to assume parallel devices, before we worked out for each individual device the Rin was around 44 ohms. Now if 2 of those are in parallel, let's assume then that's half that, so 22 ohms, which will then make twice that, 44 ohms base to base. So now we're trying to match on our input transformer 50 ohms to our 44 ohms total base to base input. Gives us an N of 1.06, which is pretty close to 1, so we'll just use 4 to 4. Our initial transformer was 3 to 4, so we'll just add another link on one side, on the primary side, and we'll make that up to 4 to 4. For the output transformer, so we worked out before that it was going to be 17.4 ohms our load resistor for each device to try and get 4 watts. So if 2 of those are in parallel, that's half that, so 8.7 ohms, and then double that, so back to 17.4 ohms collector to collector. So now we're trying to match 17.4 to 50, gives us an N of 1.695, which is pretty close to 3 to 5. So that's what we have now over here. So we've got on our input transformer 4 turns to 4 turns. Now I know this is not wound very well in terms of the spacing and the coupling, so that's not going to help our situation, but hopefully be enough for test purposes there. And our output transformer there, as we just mentioned, is 3 turns to 5. So we've got 3 turns on this side, the lower impedance side, and then 5 turns on the secondary, on the 50 ohm side. So again, same procedure as before. For those Germans, same procedure as last year, Miss Sophie. Right. So let's turn the amp on. So there we're back down to roughly our 400 milliamps total. So start to increase our power, and so that's at 10 volts, that's 0.25 milliwatts in, and we're getting roughly, it works out to be 4.2 watts, and then if I was to crank the input as much as I can possibly go, which is 20 volts peak to peak, I'm still sitting just on 5 watts. So that's our maximum output there. So certainly not as good as the previous configuration. If the calculations are right, then that should give us still a gain of 12 dB. So what I want to do now, I want to just do some more changes. I'm going to play around with replacing this input transformer here with this one here I've had lying around the junk box. So it's the style which has 2 copper tubes going through, so it's a single turn, and on one side it is, well, it's a single turn, and then it allows them to have on the inside the secondary turning. So I'm going to have the single turn on the bass side of the amplifier, and then I'll play around with the turns ratio with the primary here, or on the 50 ohm side, to see if I can't bring the impedance on the bass side much lower than our assumed values that we had before. On the output side, I'm going to stick with for now a 1:1 ratio, and then just play around using a much larger binocular style core for that one. This one here has got 5 turns to 5 turns, so just trying to increase the inductance to get up to that sort of, which I think still applies in this particular case, that rule of thumb where we want to have the inductance of, or the inductive reactance, more the point of the winding, roughly at sort of five times the load. It's not quite that, but in an effort to get it up, I've tried going 5 to 5. Again, right or wrong, and I'm certainly open to other people's experience on that one. So we'll just break there, I'll solder those in, and then we'll come back and we'll see how that performs. Okay, so for this third test, I've got a T1 set up as a 3:1, so that makes a turns ratio of 3 squared. So 50 divided by 3 squared equals 5.5 ohms, so that's 5.5 ohms base to base, so for either side is going to be half that again. T3, as we just mentioned before, will be 5 to 5. So test input, and you'll see down there 7.2 watts was the max output I get of this, and then for 250 milliwatts in, getting 5.5 watts out for a gain of 13.4 dB. So same procedure. So let's turn the amp on. Start to increase, so there goes our 10 volts peak to peak, or our 0.25 watts. So getting a good strong 5 watts there. It turns out to be 5.5 watts, and then our max gain there, so starting to creep up there to our 7.2 watts. So certainly better than the other configuration. So what I want to do now, I want to, sorry about knocking that, I'm going to just keep playing around with the input transformer T1. I'm going to leave T3 as it is. I'm now going to try making this a 2 to 1. So to make it 50 divided by 2 2s are 4. 50 divided by 4 should be 12.5. So it's going to basically double the impedance that this particular transformer is presenting, and we'll see how that looks. Back in a sec. Okay, so you can see there I just simply pulled a full link out of the T1 transformer. So now it's sitting now on 2 turns on the primary and a single turn on the secondary. So that should be now presenting 12.5 ohms between the two bases. So just testing that one again. Right, so if we bring that up to our 0.25 milliwatts input, that's now sitting on above 5 watts, and if you do the maths it turns out to be 6 watts, so another ½ watt more for the same input on the previous configuration. And then if you were to crank it up to as high as I can possibly go, do the maths on that, and that turns out to be a max output of 7.5 watts. So we've gained another 300 milliwatts, or 0.3 of a watt on the previous configuration. So it would certainly appear to be a slightly better match and a little bit more efficient. Well, a little bit more gain, more the point overall. I'm not quite sure where I want to go with this one for now. The only linkage here I could do now is to reduce that down to one link, which will be a 1-to-1. For the sake of doing a test, let's do that now. So I'll pull another link out, and we'll have a look at that, and then we'll go from there. Okay, so we can see now that the T1 transformer's got a single link coming in, a single link coming out, and as we said, the T3 transformer is exactly the same. So let's do it again. Right, that'll do. Right, so max output, let's turn it on, sorry, let's turn it on. So max output in terms of how far it goes, peaks out at, well, there it is there. That works out to be 6.2 watts. And if we come back to our 0.25 watts going in, we get 6 watts out. So that's still giving us 13.8 dB. So it's pretty close. At the lower input level, so at the 0.25 watts going in, we're getting the same output as the T1 transformer with 2 links, but the max gain is we no longer have 7.5 watts, we've only got 6 watts. So take it or leave it. So I'm going to spend a bit of time now, just have a bit of a think about what that may mean. Like I say, I'll make this one a multi-series one actually, and have some opportunities for some comments to come back and maybe try some different things. Like I say, it was more to start a dialogue and a discussion on these sorts of amplifiers and what things to look out for, I guess. I've done some experiments there, try to apply a bit of theory as best I know it, and then just sort of some logical type, well, not logical, but some intuitive style adjustments at the end to see what difference that may make. So let's have a bit of a think about it, then we'll sort of finish off, and I'll upload this and we'll go from there. And just for completeness, I did one more test. That T1 transformer, rather than just having 1 turn to 1 turn, I replaced it with a 5 turn to 5 turn. Center tapped on the secondary to provide the DC bias, and so max output, let's turn it on. Max output is 6.5 watts. Before, with the 1-to-1 link, it was 6.2 watts, and then back down to our 0.25 milliwatts in, we're getting 6.2 watts out. Before we had 6 watts, so we're getting an additional 300 milliwatts from having that, I would assume, better coupling and less losses in that input transformer. So that's interesting. Right, what I'm going to do now, I'm just going to make this into a table, and then we can have a look at it, and we'll go from there. Okay, so in table form, these were the 1, 2, 3, 4, 5, 6 tests we did with the various configurations of T1 and T3. They were the maximum output readings. They were the output power given 250 watts input, and then given that combination, that was the dB gain at that configuration. All things being equal, I guess there were sort of two just about equal firsts. This one here, where the input transformer was 2-to-1, So that should be presenting at 50 ohms divided by 4 gives us 12.5 ohms base to base, or just over 6 ohms per side. And then the output is 50 to 50. And the next one, which was pretty close as well, is essentially a 1-to-1 input and a 1-to-1 output. So 50 ohms coming in, presenting 25 ohms per side for the input, and same with the output. So yeah, I'm not quite sure what to think actually, and more than happy and really would like anybody who's got a better understanding of how these work and the design to leave some comments and hopefully help all of us. I'm not quite sure if this formula here is correct for this particular configuration, so VCC squared minus VSAT. You were saying earlier we assume VSAT equals 2 volts. I don't know if that's correct or not. It seems to be a common figure that's used. But anyway, something else potentially too, we've got 2 devices in parallel, so we've got double the input capacitance on the input, so I don't know if that's causing any grief or causing us any problems. But yeah, so I don't know if this is all correct, but all things being equal, it looks like that in this particular configuration we're only ever going to get a maximum output of that sort of, let's say 7 watts. So yeah, I'm not going to make any conclusions, I'm not going to make any definitive statements because I don't know, but I'll just sort of leave it now for comments, and more than happy to make changes and try other things with the amplifier. But I'm going to have to sort of do a bit of mulling over this one to try and think what that means for future builds moving forward, because it would be nice even just to get to start designing these amplifiers to have a formula which is about right to get things going. But for what I can see here, that's not the case. Maybe it's something to do with the maximum peak to peak swing I can get out of a 13.8 volt power supply. I don't know, I'm going to do some more reading. But anyway, so I'll just leave this video as it is, as some data collection, I guess, for people to think about, including myself for sure. And like I say, yeah, interesting times. So I'll leave it there. I'll put this up, warts and all, and we'll see, and we'll go from there. Okay, cheers all.